So today I'm going to talk about optimization challenges in machine learning and data mining, and I'm going to actually talk about the theory I wish I had, not the theory I do have. And this is joint work with, it involves some thesis work of students at RPI, Charles Bergeron, Jed Zaretsky, Gregory Moore, and Mina Shabir. And these are all, most of this was developed as part of NIH-funded research. TB Insights, a project for tuberculosis and molecular epidemiology, and Rutgers for exploratory drug discovery. So I'm going to start off. I'm going to give a little history lesson. My background is I'm a math programmer by training, and and I also do machine learning. So I'm going to look at math programming and machine learning and how they interacted together in quite a synergistic way that was incredibly beneficial to both fields. And then I'm going to talk about what I think is kind of the next wave of math programming that would really help machine learning in other areas, and give you some examples of how this is. I'll give you like 2.5 examples so it fits in the time. So I borrowed this slide from Dmitry Bertsikas. I don't know if you know him, he's at MIT, but he's one of the great senior figures in optimization today. And so he came to RPI a couple weeks ago and he gave the slide. And really, you know, mathematical programming is a much more mature field than computer science. And so the foundational work in convex optimization dates back to the early 20th century, and really after World War II it really took off, and they developed the fundamental ideas of optimality and duality that really underlie optimization today. And you know, it was developed in the 60s and 70s, and you know, there was very powerful algorithms by the 80s and 90s, and I think in the 80s and 90s they expanded it to areas in non-convex and non-smooth analysis that, well, and then it was kind of considered somewhat solved. But starting in about 2000, it was rejuvenated, and this is the word that Bertsikas uses. It was rejuvenated because of these massive large-scale optimization algorithms that were needed, and specifically machine learning was one of the primary drivers of this really emergence and interest in these algorithms, because you had to deal with massive, huge problems that you hadn't dealt with before. So if we look at kind of machine learning history, and I'm just going to skip to the end, but you know, you can look back and you can say, oh, we have perceptron algorithms, and really early machine learning, even when I was in grad school, it was all about algorithms and not about models. And there was kind of a shift in the 90s where we started looking at these methods like support vector machines, ensemble methods, online learning that could be regarded as convex optimization methods. And this really transformed the field, I think. It made it more model-based. I mean, certainly statistics was always model-based, but not machine learning. And machine learning really was revolutionized, I think, by its use of optimization techniques. And it allowed for rapid development of new methods. And so the reason why is because there was this incredible body of theory from mathematical programming that when you merge this, you know, you could just get some modeling idea in machine learning for, you know, your new support vector machine or kernel principal component analysis or whatever, and you could churn out paper after paper with all kinds of new models using existing theory and general purpose solvers developed in mathematical programming. But it rapidly became apparent that this existing theory was not enough, and so there was significant extensions. So I think the cool part of the synergism is it really stretched mathematical programming and asked it to look at things in new ways that it hadn't before. So the first thing is when you solve a machine learning model, it's only an approximation of what you really want. What you really want is to create a model that predicts the future well. And of course, this is not the criteria that you're optimizing directly. So there's no use, so you formulate some model that you want to solve and find the parameters of, but there's no use solving it to a high degree of accuracy. So before in mathematical programming, they wanted to solve it to a high degree of accuracy. Now, you just need to get in the ballpark of a good solution, and that's all you need. So what you want is methods that can find optimal solutions fast. And then also, of course, the big thing is that the problem sizes, of course, has exploded as data has exploded. So we need really high performance scalable methods. And in the literature before, they were just addressing small problems. But here, all of a sudden, you had to address massive problems. And also an emphasis was on developing special purpose algorithms. Before it was kind of general purpose algorithms, and here you want to do special purpose algorithms that exploit the highly structured nature of the machine learning problems. And lastly, machine learning put a big premium on making algorithms that you can explain and understand easily. And so, and easily implemented. So the most successful ones aren't necessarily the fastest and the best or the best theoretical convergence, but they just want ones that find good solutions fast, that are understandable, that you can implement. And so these are new criteria. So optimization has kind of been machine learning tized. Now we have new criteria for success that are somewhat more relaxed from the other ones, and I think are interesting and important. So, so in this description here, if you look at these SVM ensemble methods, these are all based on convex optimization, and there was considerable theory in the 80s and 90s on non-convex and non-smooth analysis. And so what I want to talk about is this deal right here, non-convex and non-smooth analysis. And what do I mean by that? Well, so a non-convex function is one that has multiple local minima, and a non-smooth function is one that is not differentiable. So this is a function that every paper, this is an optimization problem that every support vector machine paper that was properly written solved. This is the one you get by doing cross-validation. So when you have to pick the hyperparameters of a support vector machine, let's say it has 1, C. And so you do a cross-validation, you predict the generalization error, you train on training data, you test on testing data, and you have to pick the parameter. So you're really optimizing this function right here, and this function is highly nonlinear. You have to pick this value of C so you can put your results in your paper. And every little red dot there is a point of non-differentiability. These are kinks, so there's no gradient information there. So you need algorithms that don't require gradients or that use generalized gradients. So this theory is all about using generalized gradients. And to be honest, there's not that many people working on here, and there is no single textbook on that theory. This is not a well-developed theory or well-defined theory, but I think it's a very useful theory. So, or a useful modeling paradigm. So what I'm going to do next is I am going to, okay, well, so what I want, next time I need to convince you that we need this theory to exist. And first thing is that it could really enable the next generation of machine learning models, just like convex optimization enabled many types of models. You know, you can use linear programming, nonlinear, linear programming, quadratic programming, second-order cone programming, semi-definite programming, and people all exploited the structure of those modeling techniques to increase the capacity of machine learning to address new problems. And many of those problems are inherently non-smooth. So all of the support vector machine type functions that we use typically are non-smooth. So this is one we use epsilon in sensitive regression. This is standard SVM stuff, you know, from VATMIC. And typically you want y and f of x to be equal, and if it's within epsilon, you say fine, it's 0 error, and then you take a linear error after that. So because you have these max and absolute values, this is a non-smooth function. So we commonly use non-smooth functions now, but typically what we do is smooth them, right? But there's also many other non-smoothing functions non-smooth optimization functions that would be useful for these kind of models. And the big reason why you want to use non-smooth functions directly and not smooth them is that if you smooth them, they're inefficient. If you directly deal in the non-smooth space without smoothing the models, you get much more accurate algorithms that are much more faster and much more massively scalable. And this has already been proven in the convex case. These are both convex functions. They have linear time SVM algorithms, and they're based on non-smooth optimization theory, bundle methods, and primal dual methods. So, you can do richer models, you can do things much faster, and we need a new non-smooth convex theory and algorithms. And these models are applicable in many domains. I mean, these models are used to do things like what you pay for electricity, auctions, game theories, all kinds of areas of applicability in optimization. So it has a very general applicability, but I think machine learning is a particularly nice area to study it in. Okay, so I'm going to give you 2.5 examples from my research, So this is a project on virtual drug screening. So basically now you can do high throughput screening of drugs and to assess their activities. And they do these dose responded curves, and your job is to predict if the molecule has activity or not. And they measure, each of these wells would be maybe a different concentration for a different type of molecule. So they measure multiple concentrations, so you're fitting this data, and you fit the data here, and you find the log AC50, it's called, right here, it's called the AC50. So you just want to predict this. And no big deal, this is a regression model. So we're going to use SVM epsilon insensitive regression. Basically the idea here is you want to fit some linear function, you want all the data, this is X, this is Y, you want it to be in the tube here, and you penalize anything that falls outside of the tube. So that's what this thing does. It says I want the data in here, and if the data is not in here, then I'll penalize it as it's outside of the tube. And then also to make robust models that generalize well, I need to add some kind of regularization. So this model has two parameters. It has one, the width of the tube, which is epsilon, and it has the trade-off between the error and the regularization C. So everybody who solves an SVM regression model has to pick those two parameters in a disciplined way. Now this particular problem is a little bit harder because the data is not horribly reliable. So if your compound has activity that's not really inside this range, you can't really determine this log AC50 component. So this one right here, I mean, it could be the curve goes like this when you fit this as a sigmoid. It's called the Hill equation. But it could equally go down like this, and then this would shift it over. So this is not a reliable measurement. So we've developed ways to indicate the reliability in that measure, and so we want to design models that are robust for this unreliable data. And so a real simple way that you can do this is to divide them into reliability groups. So for each reliability group, say highly reliable data, medium, and low, or however many you want, you would have a different width of the tube and also a different C. So now you're going to have to solve this model. This is a convex optimization problem. There's just one catch. This optimization problem requires these choice of hyperparameters, and there's 2K hyperparameters. So you have to pick those 2K hyperparameters to make your SVM. Okay, the standard way that everybody does this in almost every machine learning paper is to do what's called grid search. You do cross-validation. You train on some data and you test on some other data, and you measure the generalization error, and you take your hyperparameter space and you discretize it, and you try all the different possibilities. And that's fine if you have like 2 hyperparameters, but if you have lots and lots of parameters, then this is not a feasible thing, because the number of problems you solve. So I might be solving, let's say, 10 problems for every one of these dots. I'd solve 10 optimization problems, and there'll be, the number of optimization problems that I solve grows exponentially with the number of hyperparameters. So if I have models with hyperparameters and I want to deal with the issue of model selection, I'm in essence no longer in convex optimization land. I'm solving a non-convex program, because I have to find the set of hyperparameters that optimizes my measure of my generalization error. And that's the real problem I need to solve. And then I'll use those to produce a final model that I give to predict the bioactivity of my drug to screen drugs in silico. Okay, but this is really, this is not a good theoretical algorithm just to try a bunch of points, right? This is actually an optimization problem. It's a continuous optimization. These parameters live in a continuous space, so you can formulate it as an optimization problem. So up here, you say, I would like the parameters of my optimization, I would like the weights of my support vector machines that are optimal for a fixed set of parameters C and epsilon, for a fixed choice. And I'd like to pick those so that the validation or testing set error is optimized. So really what you're solving in every support vector machine paper that does grid search is this problem. And this is a specific mathematical programming problem called a bi-level optimization problem. A bi-level optimization program is an optimization problem that has as constraints other optimization problems. So the other optimization problems are you have to be optimal on the training set for those fixed parameters. And then I find the ones that generalize best. So, so bi-level optimization is an area of study in mathematical programming. And there has been lots of work. Well, there's work, but you know, in machine learning and statistics, this goes way back to 1979, and there's been more recent work now. And so we do this initially with smooth bi-level optimization, but if you want to do it really efficiently, you use non-smooth, non-convex optimization methods. So the basic idea, the way you solve these methods, is you replace this problem right here by its optimality conditions, and then it becomes a nonlinear program. So if you replace this problem with its non-smooth optimality conditions, it's more efficient, and you can solve it. So I don't really think you're going to get the details of this in the way, but let me give the idea. So if you work in the original non-smooth space, then you have this set valued constraint for your optimization problem. You have to design methods that deal with this. And the advantage of these methods, I won't go in how they work, but the advantage of these methods is that they're much faster. So this is like a grid search that's really cheap. But the bottom line, this is time. If you use these non-smooth, non-convex optimization methods, you can solve the original problem almost as fast as you can solve the problem with hyperparameter selection. Not too much more expensive than it was to solve the original problem, okay? And this is entirely an empirical result. I know of no theory that explains that. But certainly the algorithm exists. You can do this. And the theory for non-smooth optimization really isn't in there. I mean, because you're using generalized gradients. They can't even agree what a generalized gradient is and what it means and what are the optimality conditions. So they're really not well defined. And these also are scaled on the number of hyperparameters. So it grows linearly in the size of the data and linearly in the number of hyperparameters. So the lesson here is that if I stick in a non-smooth pace, I can deal with more complex machine learning models that are more realistic, and I can still do them very rapidly. All right? And they still work just as well. So like these black lines, this is generalization area, you want it to be small, and they're among the best results there are on these problems. Okay, so here's another example of that. This is from predicting sites and metabolisms of molecules. So this is a really important problem in drug discovery. We want to pick the sites of metabolism. So we want to know which hydrogen's abstracted from here. It's going to make a metabolite. I'm interested in that because I want to know how the drug's excreted. Maybe it makes a metabolite that has a side effect. So what we do here, it's like kind of having the Olympics. You have different teams in a race, and you just know what country they're from, which is represented by the color. And all you really know is what country won. So I know, Italy won the first one, and Mexico won the second one, and Saudi Arabia won the third one. So, but I don't know which runner won, and I don't know which one is how fast they run. And that's kind of like it is with the molecule. What I do here is I have sites of metabolism, and I know that these are topologically equivalent. I can't tell the difference in the metabolite, but I know that one of these is going to be, let's say, oxidized by this ligand over here, and I know this one goes. So I want to design a model for that. So so what we do is we determine these sites of metabolism, which are metabolophores, and we make descriptors for them both at a group level and at the individual level. And I don't really have time to go into what those are, but the important thing is it kind of works like this. So you have to define a more complex machine learning model. Here are my groups of atoms that could be abstracted, and all I know is which group was abstracted. I don't know who won, and I want to make a ranking function. It's just like ranking a page in Google or something. I want to make a ranking function that picks the group that wins. And this ranking function is applied to all the different molecules. And like this group might be the same here and here. In this one it wins, but in this one it doesn't. So it's in the context of individual molecules. So, so you can pose this as a non-smooth, non-convex optimization problem. What you want is the winner, which is the highest scored member of the winning group, has to be bigger than the members of the other group. So these are maximizations of these ranking functions, and we express this as an inequality that we'd like, and then we express that using kind of standard SVM nomenclature. We express it as an optimization problem, and this is non-smooth and non-convex because we have a max in there, and also we have implied maxes here, and if you take minus a max, that is non-convex. So this is a non-smooth, non-convex problem, and we define algorithms using non-smooth, non-convex bundle methods for solving these. And you can also smooth this problem, and when you smooth it, what you have to do is add variables and constraints. So the original problem was unconstrained. It has 300 variables. The final problem is, I think it has about 10,000 variables if you smooth everything. So it behooves you to stay in the non-smooth framework. They're both non-convex. And once again, the important point is that if you stay in this non-smooth framework, you get algorithms that are linearly scalable in the size of the problem. And there is no theory that shows that that's true. It's just an empirical result. Okay, and they work just as well as other algorithms, and I won't go into that, but you can just trust me. So get this. Okay, so I'm going to just do one little teeny, well, that's pretty much it. So one last thing, I just wanted to show you that there are many other applications of this. So another thing we work on is graph drawing, and because we need to do this for our tuberculosis molecular epidemiologists. And we wanted a really simple thing. We just wanted to draw a graph where we knew the distances between all the nodes, but we wanted to draw that nicely so that they were planar graphs with no intersection with the graph with itself. So no edge crossings, we don't want node or edge crossings. And if you use a software that's out there like GraphViz or something, it will draw beautiful graphs, but they're not biologically meaningful because the distances aren't right. And we're using this for applications where we care about the distance. So, and if you do one like multi-dimensional scaling or Kamada-Kawai algorithms, you get ones that represent the distances, but they do all these extra graph crossings, and they're, these nodes live in about a 70-dimensional space. So there's many possible drawings of them that are equivalent. So why not draw one that looks pretty? So you can formulate this as a non-smooth, non-convex, a non-smooth, non-convex optimization algorithm, and you can run it, and it'll run in a second. So, and this is also, this is about a, it's probably about a 400-dimensional non-smooth, non-convex optimization problem, and we're watching, and it's drawing this graph, and it's resolving all the edge crossings, because we can express the constraint that things shouldn't intersect using non-smooth, non-convex optimization, and then optimize it, right, and preserve the distances. Okay, so that's yet another example, and you see it's trying to figure out how to move things around so that there's no intersections of the edges. It's trying to figure this one out right now. It will in a sec. And this is not real time, this is just a movie from MATLAB. There it is. So this one, and there's really, as far as the accuracy as how it represents distances, it's just as accurate as the other picture, where you start off with multi-dimensional scaling. So that's another application. So then I'm done. So basically the thing here is that I've shown to you how optimization and machine learning were very synergistic. They allowed rapid advances in machine learning because we had this existing beautiful theory. And similarly, it really stimulated mathematical programming to do advances to adjust to the requirements of these new large-scale problems. And so I think the next thing we need to work on is non-smooth optimization and non-convex optimization. And really the theory there is not what you'd like it to be. When you talk about non-smooth, non-convex optimization, there, like I said, there's no textbook. There's some Rockefeller's books from the early 90s is about it. Clark's, I mean, it's really wide open for what it can be done. And we know that from algorithms that people have written without a lot of proof, that these things can be highly scalable and linear time, beautifully structured. So I know they work, but the theory just isn't there. So I'd like to see this, and I'd like to see non-convex optimization kind of machine learning ties. Because you don't really care, in mathematical program, they're very concerned about finding the global optimal solution in a non-convex problem. We don't care. All we'd like to find is a good solution with high probability that doesn't mess us up. Because it's only approximation of the real problem, so we don't want to sweat it. So we need to do that same kind of thing to continuous non-convex optimization that they did for continuous convex optimization to kind of relax these paradigms. Okay? Thank you.
Question about your grid search at the beginning.
Uh-huh.
The replacement for it, doesn't that require that you know a function that you're learning? Doesn't that require that you know that L function? And you don't know that.
Well, so what they do is we know the L function, but we don't know the parameters, the hyperparameters of the L function. So we define an upper function where we can't have it parameterized. And we have the lower function that we solve normally in support vector machines, and that is parameterized. And normally people just fix stuff. So we're trying to find those parameters. It's just like model selection that you would do in statistics. If you're a Bayesian,